gears a little bit now and talk about another term that we haven't mentioned yet called acceleration. We defined position as where something is relative to something else. Displacement is the change in position. We define velocity as the rate of change of position. In other words, how quickly the position was changing. Acceleration is defined as a rate as well, like velocity is. But it's not a rate of change of position. Rather, acceleration is the rate of change of velocity, how quickly the velocity is changing. Acceleration doesn't tell us at all how fast something's moving. It tells us how quickly the velocity is changing. Your velocity could be really, really high, and you could have a small acceleration. Your velocity could be really, really small, and you could have a big acceleration. It says nothing about the velocity. It says everything about how quickly the velocity is changing. So let's define it as the rate of change of velocity. The symbol for acceleration is an A with a little half arrow over top of it, which means, of course, if it's got a little half arrow over top of it, it's a vector, yeah? And the units for acceleration, you would have saw this in Science 10. Anybody remember? Some people write it like this. The rate of change of velocity. The rate of change of velocity. Velocity is meters per second, and a rate is time on the bottom. So velocity, meters per second, over seconds. Does that make sense? Meters per second per second. That's the same thing, though, as saying meters per second squared. And that's usually the way that we write it, is meters per second squared. It's not wrong to say meters per second, but you just don't usually see it written that way. Some places in the world tend not to write it like this. Tends to be more like British. In Britain and British colonies tend to write it like this: ms to the minus 2. Do you know what the minus 2 is? When you see an exponent of minus 2, that means 1 over second squared. So meters times 1 over second squared, or meters per second squared. This is what we'll go with, though, meters per second squared. When is acceleration a positive value? When is it a negative value? Velocity is easy, right? Velocity is positive when you're going to the right, or going up, or going north, or going east. Negative when you're going west, or south, or down, or left. When is acceleration positive? This is tricky, because acceleration isn't positive just because you're going to the right. Andrew? When you're speeding up, yes. Sometimes, when you're speeding up in the positive direction. When you're speeding up in the positive direction. So in other words, you're speeding up as you're going to the right. Or you're speeding up as you're going to the north. Or you're speeding up as you're going to the east. Does that make sense? There is another situation where it can be positive as well. Yep. Yes, good, good. You're slowing down in the negative direction. Right? So if I'm moving to the right and speeding up, I'm accelerating in the positive direction. But if I'm moving to the left and I'm slowing down, that's the same acceleration as moving to the right and speeding up. Right? Think about that. Like right now, okay, I'll start over here. Right now, I'm walking to the right and speeding up. What does that require? It requires a force pushing on me that way, right? What if I'm a force to the right, an acceleration to the right? But what if I'm going to the left, I'm moving, and then I'm slowing down to the left? What made me slow down as I was moving to the left? A force acting on me to the right. So my acceleration, as much as I'm moving to the left, my acceleration is to the right. That means that my acceleration would be positive. So we've got speeding up in the positive direction, or we've got slowing down in the negative direction. Now, you can imagine when you're going to get a negative acceleration now, right? This is a pretty easy question now that we've identified when it's going to be positive. When are we going to slow down? When are we going to experience a negative acceleration? Anybody? Yeah? Good. If you're slowing down in the positive direction. Or, of course, when you're speeding up in the negative direction. You guys remember from Science 10 what gravity is, the acceleration of gravity is? When something experiences just gravity and it falls, it accelerates at a rate of 9.81, close. Maybe you didn't even get more specific in Science 10, I'm not sure. We don't usually say that it accelerates at 9.81 though, not in Physics 20 at least. We say that it accelerates at negative 9.81. Did you guys say negative in Science 10? No? Okay, that's fine. You just don't get quite as deep into it as we do in Physics 20, of course, right? We say the acceleration would be negative at 9.81 meters per second squared. Why is it negative? Well, because it speeds up in the downward direction, the negative direction, right? Or, listen, if I throw this board marker up into the air, what's happening to it first? What's happening to it first? It's going up, right? But what's happening to it as it goes up? It slows down in the positive direction. Okay, that gives me a negative acceleration. What happens after it reaches the top and actually stops for a brief moment? Comes back down, it speeds up in the negative direction. That's a negative acceleration, right? So any way you look at it, the acceleration is going to be negative. If the object is going up and slowing down or coming down and speeding up, the acceleration is negative, right? Is it always 9.81? Well, in the absence of air resistance or anything like that, yes, it's always 9.81. You're telling me that a feather, drop a hammer, in the absence of air resistance, the feather would fall at exactly the same rate as the hammer would? Absolutely. Absolutely it would. Now this is where it gets pretty. How many equations do we have so far circled on our data sheet as having used? 1. We labeled it A, right? Our group A equation. We're today going to learn 5 more. So all of a sudden we're going to jump from 1 equation to 6 equations that we can use. We just got to be careful going forward that we use the right equations in the right situations. Sometimes we have choices, sometimes we don't. The very first equation that we learn for acceleration comes from the definition. The acceleration is the rate of change of velocity. So we're going to say it's delta V over delta T. Next one, doesn't really matter what order we give these in because there's 5 of them, right? Next one, I'm going to say delta D is equal to VI delta T plus 1/2 A times delta T squared. Holy cow. Try using that triangle now, huh? Good luck with that. D is equal to VIT plus 1/2 AT squared. Don't worry, I'll explain this, okay? And I'll tell you how to rearrange it as well. Another one looks an awful lot like this one, actually. Delta D, actually, let me use another color because I don't want them to run together there. Delta D is equal to VFT minus 1/2 AT squared. Another one, we're going to say delta D is equal to VI plus VF over 2 all times T. And the last one that I'm going to show you here today, we're going to say is VF squared is equal to VI squared plus 2AD. Now, if you take a look at your data sheet, We already circled this one and put a little a beside it. We call that our group A equation, although we didn't really refer to that as a group A equation because it was the only one we had. Now we have 5 more equations. A is equal to delta V over delta T. D is equal to VIT plus 1 half AT squared, and so on. We're going to circle those ones and call them our group B equations. Our group B equations, these ones that we just learned, these ones that are for acceleration, are valid whenever we have an object that is accelerating, that is speeding up, that is slowing down. What we cannot use at this point, we cannot use V is equal to delta D over delta T. We can't use group A anymore, at least when we're dealing with a new problem where the object is accelerating. This equation, group A, is valid for constant or average velocity. All the problems that we've done so far have involved constant or average velocity. We'd still continue to use that equation for any problem that we've done so far. But none of the problems we've done so far have involved acceleration. New problems will. So every time you get a problem now, I want you to ask yourself, does this involve constant or average speed or velocity, or does this involve acceleration? If the answer is the first, constant or average speed or velocity, use V is equal to delta D over delta T, group A. If it involves acceleration, well, then you got to pick one of your equations from group B. Which equation? Whatever one fits your givens the best. They're all valid, just happens to be whatever one fits your givens the best. There's the general strategy and the general method. Now let's spend a little bit of time identifying what some of these variables mean and then how to rearrange these equations, because that's a bit of a challenge for us, right? Coming from Science 10 and Science 9, where oftentimes we just use that silly little triangle to rearrange an equation, right? A, that's easy enough. That stands for acceleration. And the units for that would be meters per second squared. Delta V, of course, is change in velocity. And the units for that would be meters per second. And delta T would be the time interval. And that's going to be seconds. That's easy enough, right? That's almost as easy as V is equal to delta D over delta T. Then they start getting harder, though. D, what does D stand for here? Yeah, that's displacement. What units will we measure displacement in? Yep. What does VI stand for? Yep. Initial velocity, right? It's changing now, right? It's speeding up or it's slowing down. So we have to distinguish now, not just velocity, but initial, final, whatever. This is initial velocity. And the units for that would be meters per second. Time we already identified. Delta T stands for time, right? A stands for, yeah, that's the acceleration again, of course, right? T is time. Be careful there when you're subbing numbers into this for acceleration. Sometimes acceleration is positive, sometimes it's negative. Cam, do you remember when it's negative? Yes? Good, good. So if it's either of those situations, you got to make the number for acceleration negative. It's a little tricky, but we get the hang of it after a while. D we already identified. T, A, T, we know what that is. VF is, that would be the final velocity, and that would be meters per second. In our next equation, delta D, we already know what that means. Displacement, VI, initial velocity, final velocity. T stands for time. VF here, what does that stand for? No. Oh, I knew I'd trick you on that one. I knew I'd trick you on that one. VF doesn't stand for final velocity. What does VF stand for? Final speed. Final speed, right? How do you know it's final speed there, Mia? Rather than velocity. No? No. You can have a change in velocity or a change in speed, delta. Yeah, Jacob? There's no little vector sign over it, right? Okay, so that tells us that it's speed. When we get a value for that, we calculate that, get a value for that, hey, that's the magnitude of the velocity, but it doesn't give us the direction. It only gives us the magnitude. VI would stand for the initial speed, not velocity, but the initial speed in meters per second. And of course, A is acceleration, D is displacement. Watch the signs, right? Acceleration is negative if we're speeding up in the negative direction or slowing down in the positive direction. Now, there's a lot going on the board here. We'll spend a couple of days practicing these things so that you get the hang of it. Initially, it might be a little tough, might not be, but over the next couple of days, you guys will end up having not too much trouble with this, I think. One more little thing that I want to mention before I start rearranging, though, give you the little tutorial on algebra. We always said that standard units, we could always use standard units if in doubt, right? Kilometers per hour sometimes works. Meters per second always works, right? Seconds always works. Well, sometimes we could use minutes, but seconds always works. In these equations, we must use standard units. So in other words, for displacement, we would use meters. We have to. For acceleration, we got to use meters per second squared. For time, hours, no, you got to convert it to seconds. You got to use standard units here. Yep.
For the last one, like the first equation.
Yep.
Velocity
Final speed, yeah. Yep. Yes, they are. Yeah. Yeah, I'm not sure why we write it in that form as opposed to solving for, say, VF. But that's usually the way you end up seeing it, including on your data sheet. So we'll continue to write it that way, and then we'll just rearrange it to solve for whatever. Okay? Okay, let me give you, before I give you any real example problems, let me give you a little tutorial on algebra, okay? Because this is where some of us struggle a little bit, is with algebra. We do it in math class, and we do well in math class. And then all of a sudden when we switch classes and go to physics and you have to do the same thing effectively, you're like, oh, I don't know what to do. Because you forget. As soon as you leave your math class, it seems, you forget how to do it. Plus, this is a little bit more concrete, a little bit more meaningful than maybe sometimes what you do in math class, which is, you know, just X's and Y's and whatever, as opposed to actual variables. Sometimes that confuses us a little bit as well. All right, the general rule for rearranging equations, general rules for rearranging equations is this. And there's little subtle things that we have to add into the mix, but there's only a couple real important rules. Number one, get rid of what is not attached. Get rid of what is not attached. And then get rid of what is attached. How do we get rid of what's not attached? Do the opposite. If I add something to x, it's not attached. I would get rid of it by subtracting. If I divide something by x, that's attached to x. I would get rid of it by multiplying. If I subtract something from x, that's not attached. I would get rid of it by, what's the opposite of subtract? Add. If I multiply something by x and I want to get rid of it, that is attached to x. I would get rid of it by dividing. So we all, I think for the most part, get that. It's just a matter of what we do first. That's what people struggle with. What you do first is what's not attached. If it's added or subtracted, then it's not attached. We get rid of that first. If it's multiplied or divided, then that is attached, and we get rid of that second. Now, there's little things with brackets and squares and square roots and whatever, but this is the thrust, the bulk of most of what you ever have to do with rearranging. We'll deal with those little subtle different things with square roots and so on as we come to them. So let's take an equation. Let's say D is equal to VIT plus 1/2 AT squared. And let's solve for VI. Holy cow, right off the top, a tough one. Let's solve for VI. Get rid of what's not attached. What's not attached to the VI? What's not attached are into the VI?
1/2 acceleration times square.
Good. This whole thing, right? Half isn't attached. A isn't attached. The t squared isn't attached, right? Because they're all attached together, we can kind of treat them as one thing. We'll say that whole thing is not attached. Okay. So how do you get rid of it? It's added to VIT, so we're going to get rid of it by subtracting, right? So we're going to say D minus 1/2 AT squared equals VI times T. Make sense? We just subtract that entire term. We're still not done, but man, are we ever a lot closer. Might go, what do we got left with here? The T, that's the only thing that's now with the VI, right? Is that attached or not attached? That's attached. Right? You know what, honestly, at this point, it doesn't really matter because it's only the one thing, right? We got rid of what's not attached. Now we got what is attached. How do we get rid of the T that is attached to it? We divide it, right? Because it's multiplied. Really what we're doing here is subtracting 1/2 AT squared from both sides, right? But we're just kind of skipping a step there. Divide by T. Oh, man, this looks a little ugly, but we have to divide the entire left side by T. So don't just say D over T minus 1/2 AT squared. It's D minus 1/2 AT squared over T. Got it? That doesn't seem that hard, does it? Isn't that easier than a triangle? Maybe not easier than a triangle, but it's close. Let's try another one. Let's try another one here. Let's go with VF squared is equal to VI squared plus 2AD. I want to solve for delta D. Remember the rules. Get rid of what's not attached. What's not attached to the delta D? VI squared. Okay, how do we get rid of VI squared? Take it over by subtraction. So it's going to be VF squared minus VI squared. Really, we're subtracting it from both sides, but we're just not showing everything there. Now the 2 and the A are both attached to the D, right? Which one do you want to get rid of first, the 2 or the A? Why don't we just get rid of them both together? They're both attached in the same way, so just get rid of them both together. How do we get rid of them, Ben? Yeah, they're multiplied by D, so let's take them over by dividing. Now be careful, it's not VF squared over 2A minus VI squared, right? That's wrong. What is it? Yes, VF squared minus VI squared over 2A is equal to delta D. That kind of making sense? Okay, let's do one more that involves a square root here. Let's solve for VI. Let's solve for VI here. Get rid of what's not attached. What's not attached to VI? What's not attached? 2AD, right? And how do we get rid of it? Do the opposite. It's added, so it's subtracted. Let's say VF squared minus 2AD equals VI squared. Still solving for VI, right? Well, now we're left with VI squared. What's the opposite of squared? We consider that squared like an attached, right? The squared is attached to it, so we get rid of that last. And then let's do the opposite, just like we divided when it was multiplied, we divided to do the opposite and so on. We're going to square root this. So it becomes VF squared minus 2AD square root the whole thing equals VI. You guys looking at this right now saying, like, why did they even bother teaching us that triangle in grade 8 or grade 9? We could have handled this, right? You could have easily handled this in grade 8 or grade 9. Get rid of what is attached, then get rid of what isn't attached. How do you get rid of them? Doing the opposite. Yeah, Marty?
For this one, solve for everything inside the square root.
Yeah. What I would do, unless you're really good with brackets on your calculator, do it one step at a time. Punch whatever VI is squared equals in your calculator, and then say 2 times A times D in your calculators equals, and then subtract the 2, press equals, and then square root that number. As you get better with your calculators, you're going to be able to start using brackets better and kind of do it in less steps. But right now, that's what I would do. Unless you, right now, are really, really good with brackets on your calculator. Good? Let's try to do one example here before the end of class here, see if we can get one in. Here's example number 8 in your booklet. It says a car traveling at 10 meters per second accelerates to get past another car. If it speeds up to a velocity of 25 meters per second times 6 seconds, what's the acceleration of the car? Hey, is this a group A problem or a group B problem? This is definitely a group B where it's acceleration, right? What is this 10 meters per second thing? Yeah, that would be VI, the initial velocity. VF would therefore be equal to 25 meters per second. And my time interval here would be 6.0 seconds. We want to find the acceleration. Now, go to your data sheet. We have 5 group B equations. Which one looks like it fits the best? Hold on, let me just finish this up, okay? Which one looks like it fits the best? They're all valid. If you try any of the ones circled in green there, they're not going to lead you astray. But what they might do is lead you to no answer. You just can't solve for an answer. Which one looks like it fits the equation or the givens the best, and therefore will lead me to an answer the easiest? Which one looks like it fits the best? We have T, we have VI, we have VF. Yep. VI plus VF over 2 times T. Okay, VI, VF, yeah, T. Oh, that would give us D, not A though, right? Is that wrong? No. We're allowed to solve for D. It's just not what we're looking for here. Cam? Yeah, A is equal to delta V over delta T. That's the one that I want to use, I think. But listen, it's okay to try one of the other ones. You get delta D, that's fine. Just keep going, right? A is equal to delta V over delta T. Delta V is VF minus VI, or 25 minus 10, over 6.0 seconds, and that gives me 15 over 6, which is 2.5 meters per second squared. Does that make sense? Okay, I'm going to ask you guys just to try on worksheet number 4 tonight, just the first question. Just the first question. I wanted to get another example here, so I'm not going to assign lots of questions. Just one to see if you can handle it, all right? Have a good night, guys. Quiz tomorrow, and worksheet number 4, question number 1.